Yeah, good.
Hello again, thanks for being there. So Charlie is the next speaker. He's a member of the runtime team at IBM, and we'll talk about Ruby and OMR.
Thanks everyone, I'm happy to be here and talking about Ruby and OMR. I'm glad that we got the invite. So a little bit about me. You can reach me on Twitter or email. As we come up with new things or things are happening with OMR or our Ruby preview, OMR preview, we're tweeting about it all the time. So there's lots of stuff there. For me, my background is I've been working on IBM's Java virtual machine and runtime technologies for about 11 years now, maybe 12. Can't remember when I started, it's too long ago. And most of my focus has been on garbage collection scalability, and lately it's been on making our technologies available in our own for the OMR project. So my talk today is on the Ruby and OMR, so I figure I'd start with a bit of overview on actually what OMR is for people who've never heard of it, which is probably most people because it's new and not even really out there yet. So it's an open source toolkit for language runtimes. So what this means is we want to actually extract the language agnostic components from our JVM technology out of the JVM and provide them so that other languages could use them as part of their language. This is sort of a simplified view of a runtime. And the thing is with this picture is you'll see that a lot of the actual components we believe can be actually abstracted out and consumed and shared between multiple runtimes. So examples of this would be the garbage collection technology, the just-in-time compiler, our diagnostic services for gathering stats and things at runtime or post-mortem, and also our platform abstraction layer. So our VM has a long history starting back in the Smalltalk days, so we actually still have some of the code in our VM as a code originally from our Smalltalk virtual machine. And because we've been working for IBM and doing embedded VMs and server class VMs, we've actually had to support all kinds of different platforms like the IBM PowerPC, ZOS mainframes, all kinds of embedded platforms for our MEVMs back in the day. So ARM, MIPS, all of these things we've been able to support. So we actually have a very well-defined porting library that you can use to actually bootstrap bringing up a new runtime. So that was a quick overview on OMR, and now I'll start talking about the Ruby and OMR preview. So the Ruby OMR preview was talked about at Ruby Kaigi for the first time by a few of my colleagues. There were two talks. The first one was on a deep dive on the GC technology that we're providing in OMR and how we've actually incorporated that into the Ruby VM. And the second one was on the JIT technology. You can find these talks at those links, and I believe they have videos. We've actually pushed our preview to GitHub, so you can download it, use it, actually try out our Ruby VM. That's the link. Due to not being able to actually have our OMR code available as open source project right now, we've provided binaries in Docker images so that you can pick them up and use it quickly. That being said, inside the Docker image, we actually do have a full Git clone of the Ruby repo, including all of the changes we made to MRI. It just doesn't include our OMR source. You can't quite build it right now and use it, but as soon as we actually make our OMR project available on GitHub, this is something that you would actually be able to go and download and actually compile it yourself. It's currently available, the Docker images, for 3 different platforms: Linux x86, Linux Z, and Linux on Open Power. They're all 64-bit versions of those platforms. The Ruby OMR preview is based on Ruby 2.2.3. If you actually look at some of our notes on the wiki page, we were on 2.1 and we went to move up to 2.2.3. We actually, 2.1 we went to move up to 2.2.3. The guys doing the merge actually merged in the wrong direction, so the patch is kind of a bit of a mess in there. We're working on cleaning that up and actually merging to the master branch so that we can have support for new things. We've passed all of the main tests and everything that all the tests is shipped with MRI, and we can still run Rails apps. So the components we've integrated so far from OMR are our garbage collector. Because Ruby doesn't support object movement, we've actually only brought in our mark sweep technology at this point. We have not actually plugged in our compactor or our generational collectors or any of our other technology, because we want to keep Ruby and all of the C extensions working. We plugged in the just-in-time compiler, and we plugged in a bunch of our diagnostic tooling. Most of the diagnostic tooling actually comes for free by just consuming the other components. So now I'm going to take a step into the garbage collection technology we've provided in the preview. So our strategy with introducing all of our components into it was to always be 100% compatible with MRI. We don't want to break any C extensions. If you can run your application on MRI, this is actually still MRI. It's just we've changed some of the components out from underneath. So everything should continue to work. We wanted to decrease the pause times. Ruby actually has made a very significant advancements in their garbage collection technology across the last couple of releases. But we feel like we can still make some improvements there with things like parallelism. We want to increase the allocation speed of allocating objects, and we wanted to improve object locality. So for the 100% compatible, we did not want to break the C extensions, continue passing all tests, and then run a bunch of the third-party tests to just make sure that we haven't broken anything. The big thing for us plugging in our technology was to keep C extensions working, we actually had to continue to conservatively mark the C stacks. So MRI actually doesn't have a precise GC. They do conservative marking, so that means for when you call it into a C extension, any objects that are referenced through there, or you may fetch a field out of an object while you're in the C extension, you actually have to go scan the C stacks, and anything that looks like an object pointer, so it's in the heap and has proper alignment, you just consider to be that object is alive. And we couldn't move objects. So to decrease the pause times, when we plugged in our garbage collector, the first thing that we got for free was parallelism. So Ruby has a well-defined root set. So the first thing we did is we actually just divided up, looked at a bunch of the roots, seen which ones could be processed in parallel with other roots, which ones couldn't, those types of things. And then actually we just go and process those roots in parallel. The next thing is just by using OMR, every object we marked through root processing, the next phase, as soon as we were done roots, we just went into our complete scanning phase, and that actually will just go again and in parallel use our work stacks, which are very highly parallel. It can scale up to 64, 100 CPUs at times, depending on the workload, and use that. We actually we were able to perform some of the object finalization in Ruby in parallel. So there's actually two types of finalization in MRI. Objects can have their own finalized defined on them, And in also objects, if they're too large to fit in the fixed object heap, for MRI, they actually will allocate data off heap, which I'll talk a bit more about later. And those objects have to actually then, when they die, you have to actually go free that memory associated with them. So we want to be able to run a bunch of these things in parallel as well. And then the last step was doing sweep, of course, in parallel. By doing a bunch of the work in parallel, we're able to drastically cut down the pause times. But this is when you actually have a reasonably large live set. If you're talking 1 megabyte total heap size for all of the data you're using, it's actually very difficult to get enough work to parallelize that. So if you have a 1 meg heap and you're starting to talk about a couple 100 kilobytes of live set after each GC, you actually don't get very much wins from running things in parallel. And actually, we won't actually use more than 1 or 2 threads. We have some algorithms to pick based on your heap size and the history of how much you're keeping alive on how many GC threads we'll actually use for an operation. Because if you use too many, you actually just spend all of your time synchronizing the threads, and it's worse than actually just doing 1 thread. So the next thing was to increase allocation speed. So with OMR, and from our Java days, what we actually do is we have something called a TLH. This represents thread local heap. So when the thread needs to allocate an object, it won't actually go and all the way out to the heap and allocate one single object and come back in and keep going. If you have multiple threads and running things in parallel, which MRI has a GIL, so that's not quite there, you don't want to be hitting the heap block all the time. So what this does is you get a large chunk of memory when you need to allocate, and then you can just bump pointer allocate out of that because your thread is the only one that will allocate out of it, and keep going. And eventually, when you fill that block up, you just go get another block and so on. So the allocate code for allocating an object, and this is some pseudocode here, is very simple and straightforward to actually allocate. So this could be right in, if your bytecodes have like a new bytecode, or if you go and have a generic allocate location for them, all you have to do is off of your thread, check to see if its TLH has room for this object. If it does, you use that pointer for alloc, and then you just increment alloc by the size. And if you're full or you don't have room, you can call the slow path to go allocate, and that will do any refreshes or whatever needs to be done for the TLH. Yep.
What's the difference between a TLH and a TLAB? Or is it just different names?
The question is, what's the difference between a TLH and a TLAB? They're basically the exact same thing as far as I know. Not actually allowed to look at the Oracle source code. I just going from what I see in docs and white papers, I'm pretty sure it's very similar. So we basically just brought that over to Ruby. The one note is that the OMR heap by default has a minimum free list entry size of 512 bytes. So anytime you get a TLH, you'll get at least 512 bytes to allocate out of. And there's some growth algorithms and those types of things to be able to pick more appropriate sizes. So that after that, when we were still looking at some of our performance measurements and running, we noticed that, and this is where I'll cover a bit more, in MRI, that they use all of their objects are the same size. So they divide the heap into a bunch of fixed size cells, and all objects are allocated there. If you have an object that actually requires more space than that, they go in malloc memory off heap, and that's what you use for your data section of the object. So very quickly, if you think about something like a string that has, we'll go with 30 characters or 24 characters, you're going to have your string object, and then you're just going to have a pointer to this off heap data where actually the char data lives for that string. So anytime you're actually doing anything with the string, you have to go fetch through this pointer, which we haven't got rid of that with our OMR buffers, but you're actually going to read memory off the heap somewhere else. So that memory could be anywhere in malloc space and is almost certainly not close to the object on the heap. So what we've decided to do is actually create what we call an OMR buffer. It's just another, it's a type of object we've created for Ruby. Anytime that an object needs off-heap memory, we'll just go allocate an object of this type, and it actually stores a pointer into the data section of this, just past the object header. This means that in a normal path for doing a lot of the object allocations, like say creating a string, you create the string object and then go get the backing store. If this memory are being allocated out of our TLHs, that string object is directly followed by your OMR buffer. So in this case, a lot of your objects, the data is following directly behind. So that gives you a lot more improved object locality. The other benefit of these OMR buffers is that since they're just objects on the heap, and they have a reference from their object that's consuming them, they will actually just get collected and cleaned up as part of normal mark and sweep. So we actually do not need to actually go and explicitly free them. So again, I'll come back to decreased pause times. One of the largest parts of the pause time, we're actually going to free all of this data. In MRI, they actually walk every single dead object and call object free on it. We were keeping track and doing something similar, which meant that we actually had to visit all the dead objects. It's kind of counterintuitive to what you normally want to do in a GC. Normally you actually want to not visit the dead objects. They're dead, you don't want to go touch them. You don't want to bring that memory back into your caches and those types of things. So this actually, by them just being collected as part of our normal mark sweep, we don't have to go call any free, actually significantly reduce that part of the pause time. And in our stop the world collects, that was making up on average usually 80 to 90% of our pause time. So they got cut by that much immediately. So MRI made the decision to actually use fixed size objects for a reason in its fragmentation. So all of their objects are the same size. That means that anytime an object dies and they have a fruitless entry, you can always allocate another object in there. Now that we've moved the the data sections on the heap, we now actually have variable size objects. So that actually can lead to fragmentation on the heap, which means in other types of languages like Java, you would actually run a compact or something to actually get that back, but we can't move objects here. So you're kind of stuck with this fragmentation. What we're looking at doing to try and alleviate this is bring some more of our heap technology from Java into OMR. So we have a real-time garbage collector in Java that uses a cell-based heap. So we're actually looking at bringing that in, and that would actually help alleviate the fragmentation. The other thing we're looking at adding is our concurrent marking from Java. So right now we just do complete stop the world collections, but what we want to do is actually bring the concurrent collection over where the marking phase can actually happen concurrently with your application. That would happen by the application threads themselves paying a tax, similar to how MRI does their incremental GC right now. But also we'd be able to have our background threads spin up and actually be able to go through and complete a bunch of the work at the same time. MRI has the appropriate object access barriers, so it's just a matter of plugging it in and getting it going once we have it in OMR. So we're expecting to have that within a month or two of us actually open sourcing the project. So that's it for the GC stuff that we've done for MRI, and I'd like to move on now to JIT. So the strategy for the JIT was to basically mimic the interpreter for compatibility's sake. So what that means is if you're executing in the interpreter and you're going to keep this, push this to the stack and keep up all these values in the stack and in the thread, they actually update them all the time in the JIT, and that's just so that we can actually fall back to the interpreter at any time we want. So they implement a bunch of these simple opcodes directly in IL, and any bytecode that they actually, that's a lot more work, we actually generate during compilation of the VM. So MRI actually generates the interpreter loop from an instruction definition file. So while that's being generated, any of the bytecodes or opcodes that we care about that we're not going to be able to JIT, we actually just have it generate a function that we can call directly from the JIT. With this, we can do things like, in a bunch of cases, we can fast pass some of the checks. So something like the trace bytecode, what you're doing most of the time is checking, is trace enabled? If so, call trace. We don't want to actually implement all of the trace bytecode. So what we do is we actually just have IL for doing the quick check, is trace enabled. If it is, call the VM helper. If not, just keep going. So that allows us to fast path a bunch of different patterns. And again, we're not trying to handle everything that the interpreter is doing right now. In the future, we want to keep adding support. But in our first pass was just getting everything going. So we don't handle any of the really hard cases. And some of the opcodes are actually turn into like 1,000 lines of instructions. So those are things we'll move forward to as we get closer. So right now, the JIT support in the previews that you can download and use, actually, they support almost all the bytecodes. Sad to say that it doesn't support all of the bytecodes, but we're still working on it. And you can actually, the only thing that happens is if they don't support a bytecode, it will actually fail to JIT that given iSequence when they're trying to compile. Doing most apps and like starting out Rails and running it, you will only see a few methods at the beginning that fail to compile. Everything else actually gets compiled as we go through. We basically compile iSequences after they've been executed a certain number of times. By default, I believe the number is 100, but that's something that's easily configured by the command line. You can just tell it how many. And then we actually dispatch to that JIT code through the normal VM exec bytecodes. So they would go to the exit, jump to run a method. We actually just check to see has that iSequence been compiled. If it is, go execute the JIT code. So the future work that the JIT team is trying to get going now in Ruby is they want to start adding some speculative optimizations. We have a very rich set of optimizations coming from the Java side. And one note is our JIT technology that we have isn't only from Java. It's actually used to build their COBOL compiler. It's used parts of it for XLC's backend. It's used for a bunch of different compilation technologies, so it has a very rich set of optimizations available to us. So they're hoping to add things like some class hierarchy optimizations. They want to add recompilation. So right now, there's one chance to JIT a method. There's no profiling in the interpreter or in the JIT code. So they want to get that stuff added as well so that they can make the right decisions on, or improve the decisions on what they're JITting and the types of code they're doing. All of the JIT compilation is synchronous right now. So when that count gets down to 0, they would stop at that point, go JIT the method, and come back and then execute the JIT method. What we like to actually do is have like another compilation thread or something on the side that we could just sort of queue up work units and say, go compile this. And then when the next time somebody's going to run, they just get, if it's compiled, they would see it. And they really want to bring more of the optimizations. They're at about 10. I think they've added one more since I was talking to them last, maybe. But we really want to get this in. and start really making some improvements on what we can do in Ruby. So I'll quickly go through some of the diagnostic tooling that you get now with their preview. So garbage collection and memory visualizer, GCMV. This basically is a post-mortem debugging tool. That's for looking at your verbose GC logs. You can download the tool from this link. The exact same tool works with IBM's JDK. It works with IBM's Node.js port. And it also works with this Ruby OMR preview. The tool doesn't need any changes to work with these. And by just plugging in the GC to Ruby, I made no changes to anything, and you actually get the full-on verbose GC, very similar to the Java output that this tool can use. Here's an example of the tool, the types of data you can see. Other than just actually visualizing the data, there's actually a report tab. It will actually make some suggestions on some tuning options that maybe you want to try. Those right now are more tuned towards larger applications and server type applications from Java, so one of the common recommendations with Ruby is to run with a larger heap. I'm not sure that's always the best answer, but those will be tweaked as we keep going forward. Another one is Health Center. This can give you a live view of your application as it's running. So you attach to an agent that's running with your runtime, and it'll actually just give you a bunch of data live as it's going. Again, the same thing. It works with all the runtimes that we work on. It will actually have a bunch of different tabs. You can get CPU information about what the CPUs are doing on your system, how much they're consuming, what's going on there. You can get garbage collection data, which is the tab I have open here. It's basically the same type of data that you would see for GCMV, but it's actually happening live while your system's running. So you can watch for spikes and what's going on.
Is there impact on performance when you run this?
Health Center for the GC stuff, no. I believe the overall performance goal was around 1%. I'd have to actually measure what it's at right now and find out, but it's about 1% overhead. In the Java space, a lot of customers actually just run with the agent all the time and will attach if they have things happening, and are usually willing to pay the 1%. The other thing we did is we actually have Ruby method profiling available as part of this. So with a very small amount of code changes into Ruby, you can actually get and see all of the Ruby methods that are going, the time that they're spending, time spent from the tree they're in. This is sample based, so it's not 100% accurate. And the sample time is based on keeping that performance low. But for most of the things I've looked at, the profiles are quite accurate and very good. And you can see all kinds of interesting data on it there. And another tab that's there is sort of on native memory. So anything that's allocated through our OMR libraries as far as native memory is concerned will show up there, and you can see what components and the breakdown of all the native memory you had. So as if a language like Ruby didn't make any calls to malloc, but called through our port library for malloc to get memory and those things, it would all start being tracked 100% that you can see in this tab. All right, so some performance results. The other guys in here with Truffle and Grawl and JRuby, they were throwing up some 30x numbers. I'm not going to throw up 30x right now. So is Ruby fast yet? That number is about 8 to 10%, but that's only with the interpreter. So I put this one up to specifically call out the GC changes. So the change that actually added this performance was moving the object data on the heap. So just basically the locality of your objects being closer, the objects being closer together, actually gives you on some Rails apps and things about 8-10% throughput all on its own. The next one, these numbers are all with the JIT. This is a bunch of benchmarks, I believe from Bench 9000, but I may be mistaken on which ones they're from. So these are running with the JIT. You can see that a few benchmarks we're on par, maybe a little lower than just with the stock Ruby. But there are a bunch where we're actually 1.5, 2x, approaching 3x on some benchmarks. So this is without any real tuning for Ruby at this point. We've just got it working. So we're hoping now that we can step up the actual optimizing for Ruby, getting some more optimizations, and maybe some Ruby specific ones in to actually help drive this number up a lot higher. So as a quick example of just a smaller micro benchmark that I sort of wrote on my own, it's basically calling power 2 to the n in a loop. I think the loop was 600 million times or something like that. The time taken to do this is in seconds. So on stock Ruby, it was taking almost 30 seconds, and with the JIT running, we're down to almost 5. So it's almost a 6x improvement on this. This is just to show that for some simple things like where Ruby's doing, if you're using math operations and stuff, and it's all in Ruby code, the JIT, even with our simplistic view of the world right now, can actually provide some pretty significant improvements. Yeah, lower's better on this one, but so on the future of what we're going to do here, we're really looking for feedback from the Ruby community. They presented at Ruby Kaigi. They got to sit down and talk with Mats and some of the core Ruby guys. Lots of interesting conversations. But we want more than just them to provide us feedback. We want people that are actually using Ruby all the time in their applications, playing with it, doing things. When we first put the preview up, there were some people opened issues. So it's on GitHub. That was the first link that was to GitHub. Open issues there if you want. We've already answered a bunch of issues, fixed a problem. Somebody actually found a problem in our stuff, so we fixed it right away. We're going to be very responsive to that. And once we get all the code out, we'll be responsive for all of the project. But we really like to get a bunch more people looking at this, telling us about applications they're running where they're like, oh, you're the same speed or slower. We're hoping that's not the case for a lot, but we want more examples of the types of things people are really using. We want to actually get involved with the Ruby community to actually see what we can do. And now that we're publicly talking about this, it's actually a lot easier. Before it was difficult to ask the Ruby dev team questions, and there's some areas that we even wanted some detail so we could make some optimizations. It was difficult to ask them for help because if they asked us why, we weren't allowed to really tell them why we were doing things. But now that we're open, this should become a lot more easier. And if the Ruby community believes that there's parts here that can actually help, we'd actually like to help with their Ruby 3x3 plan. If anybody's seen any of Matt's talks, the last one or two, he throws up a IBM J9 question mark slide. The answer is yes, we actually do want to help. We want to be involved with going forward. Some of the things that we've noticed about MRI as we were digging through that kind of limit what we're able to do in certain areas and things that we wanted to discuss or hear other people's ideas on is the GIL or GVL. With the GVL, it's very difficult to actually have multiple threads and scale up just because you can only have one thread really active at any given time. We'd like to work on removing the GIL or at least reducing the impact or the times where you have to hold it. But the other thing is how much code would be broken with that. So there's some major trade-offs here. So we really want to sit down and talk to the community to see what people would think about that. Would you be willing to trade 4x, 16x on a bigger machine throughput improvement on via scaling and have to redo some of your C extensions or actually add some locking to your code and things? Another one would be improve C extension APIs. Right now, the fact that that MRI just hands out a direct pointer to the object and people can fetch fields out of it, write to it, do whatever they want, it basically means you can't do any object movement. in a lot of the other runtimes, the highest performant garbage collector is always a copying generational collector. You see most in any of the big scaling VMs, that's what they're using. You can't use that here because we can't move objects. And then also, it would probably open up some JIT optimizations as well if we weren't handing out direct pointers. Again, how much code would be broken, so those are things we have to look into. And the other one is, since MRI didn't have a JIT, the fastest way they can optimize some of the code is actually to keep a lot of their class libraries written in C code. It's not actually written in Ruby for a lot of it. All of those class libraries that are actually, and especially the core ones that are actually just implemented in C, basically block our JIT from doing any optimization. So for the JIT to really get in and do a lot, if some of these key classes were actually turned around and written in Ruby, it would really help us out. Thank you guys for letting me talk about our project here, and open for any questions on anything.
Now, Ruby is used as example for this OMR framework, but are there other languages that have been used with this OMR?
So the question was, Ruby is used as an example, language consuming OMR. Are there any other languages? So our Java 8 product and Java 9 product, Java 8 shipped using OMR. Java 9 is being developed in conjunction with OMR. So you all know that works because that's where we're taking the code from. We've done MRI. We've also plugged it into CPython. We have some mixed results on CPython related to the fact that they use reference counting to keep things alive. And personally, I've also spent time working with SOM language, and they have a C and a C++ implementation. So I've actually spent time hooking OMR up into that just to sort of help us define some of our APIs. But we want to go forward and talk to other communities like the Node community for V8. And now that other companies are talking about having sort of an open standard there for having maybe multiple VMs working under Node, that's sort of opening up a lot of doors in communication for us as well.
And in the past there have been some initiatives to accelerate Java in hardware, like in Silicon. Java acceleration in Silicon. So some parts of OMR maybe could be accelerated by synthesizing it to hardware?
So the question was on whether or not parts of OMR could be sped up by hardware acceleration. There's areas for certain things we've looked into. It's not quite along the line, but we've looked at things like GPU and FPGA for doing some offloading to some of those things. OMR, when it ships, will actually have full-on offload support to GPU because we added that to Java, so you can actually send a bunch of your work off to be executed on GPUs as long as you're following the right constructs for that. But that's sort of the extent of where we got to now. But that's sort of the idea with what we want to do with getting the technology out there, is that if we have it out there and a bunch of languages are consuming it, if we do add some key feature like that or something to it, any language consuming it, it should be very easy to bring that up in those other languages that are consuming it there as well.
I have a question on GC.
Yeah.
What do you mean by in MRI you can't move objects? What do you mean move objects in GC?
So what I mean, the question was, what do I mean by you can't move objects in MRI during the garbage collection? So on the heap in objects in MRI, for things like the VM itself and C extensions, they actually, JS will constantly be holding pointers to the objects in local variables and things.
Yeah.
So at that point, if we move the object, that is going to be holding a stale pointer, so they would be now accessing invalid memory.
Yeah, like if you replace the pointer.
So if we could go and replace every pointer everywhere, you could do it. We actually spent some time working on getting the Ruby VM the ability to compact. And we actually were successful in that, so we can compact and move objects around inside the interpreter was talking to, and a few C extensions. But the problem where there was a lot of C extensions that are just totally assuming that objects will always, they'll never move. So all of those C extensions were immediately broken.
Okay.
So to keep our compatibility, we backed off on the compaction.
Also, continuing this, did you consider to use like features of Linux kernel where you can move the physical page? Like the virtual address is still the same, but you can compact memory by replacing the actual physical page.
So the question was, have we thought about using some sort of OS tricks to be able to move the physical pages but keep the virtual pages the same? We've looked into that at high level and for other things, but it's not something we've really progressed on at this point.
Okay, thank you.
Just 1 second, back in the back.
I'm curious what license IBM plans to release this stuff under. Do you know?
See, I really feel like my first slide was gone. I think I hit delete instead of arrow down on my one of my first slides. So the Eclipse project will be released under EPL right now, the Eclipse public license. But actually, we have a request into the Eclipse committee to actually allow us to dual license as EPL and Apache.
When you talk about the buffers that it is placed right behind the object.
Yep.
So does it support some kind of object inlining, or how is it done that stays right behind the?
So the question was about object buffers and their locality to the object. So most of the time it's directly following it, but if say you grew it, if the buffer had to grow after the first time you allocate, that would be somewhere else on the heap. We don't do anything to try and move it closer or grow it that way. But in practice, outside of some of the hash tables and stuff, a lot of the off-heap data was used for strings in a lot of cases, so they didn't tend to be growing as often, but they still do. And a lot of things are in sockets grow.
Okay, so if you have a garbage collector which would be moving objects, how would you ensure that it's moved together?
So the question is, how would you ensure they're moved together if you had a moving garbage collector? So some of our other technology does this in Java even, and it will actually sort of do depth first, which in this case that would be the only field, so it would tend to be copied directly behind it. But again, it's a best effort because we can't always guarantee there's space directly following it and how we copy. But yeah, in our moving collectors, it is frequently following it again.
Question related to the garbage collector. I used to work on a project. It was with a Skelmer GVM, and it was running on Zettelbooks with limited hard resource. And we were seeing issues that when the garbage collector kicks in, that it's consuming a lot of CPU. It was like a box doing DVR recordings, video recordings, several HD channels, and the garbage collector was actually causing issues because it was taking up CPU space. And then we were questioning if there are no means to schedule something that when a certain threshold of the memory is consumed, that you can schedule the garbage collector to come up and release this, but only release this when the CPU load is lower, so that it would not make the CPU hits up to the roof. Or that kind of level of control. You can control the garbage collector in some kind of way to make it more intelligent, and to kick in only when it's not going to screw up all the things.
So the question is about GC pauses getting in the way of work and consuming of CPU, possibly starving out other processes running on the same machine. So there are a few things. So with a lot of the technologies, when we have the concurrent collectors, you can sort of tweak the time that they will kick off so that they will start collecting. And because they're doing a lot of work concurrently, you can kind of meter what they're doing at that point. Because if you're only allowing the application thread to pay tax to do the collection and no background threads, you will still only consume about the same amount of CPU you are consuming while you allocate or while your allocation is running. So that's one way, but that's not ideal. In our Java VM and technology we're hoping to get open source as well, we have sort of a real-time garbage collector. So that guarantees that it's an incremental collector and any given pause is no more than X milliseconds long, where by default that's 3 in Java. But again, it's still, that could get kicked off and do those increments all the time, but there's no great answers to do it other than really calling GCs, but that's still not great. Like, you could force a GC anytime you want, but it's not really a great answer. Sorry, I just got the time up. Like, I'm around. You guys can find me anywhere over the next couple hours, and I'm willing to talk more.
Yeah, thank you.